So let's have a look at this area question from the 2015 Junior Short Higher Level Sample Paper 1. It's a question about squares. We're given a large square of side length 10, and inside of it we have two smaller shaded squares. The question is to find the smallest possible value for the sum of the areas of these shaded squares. These shaded squares change in size as we move A, this movable point, up and down this diagonal. So to demonstrate how the squares change in size as we move A, let's move A diagonally down to the left, and we can see that this square on the bottom left hand side will become smaller, and the square that was on the top right hand side has become a good bit bigger. And again, the question is, as we move A up and down the diagonal, what's the smallest that we can make the sum of these shaded squares? So to add a little bit of understanding to the question, let's put some dimensions on these shaded squares. So the smaller square on the bottom left, I'm going to give a side length x, and the larger square on the top right, I'm going to give a side length y. Now I say smaller and larger, but remember, we'd be moving this point A up and down the diagonal, so that there is a possibility that this square down the bottom left hand side will actually become bigger than this square on the top right if x moves and gets to be a size large enough. Okay, so now that we have values on the dimensions x and y for the two squares, let's find a formula for the sum of the areas of these squares. So if we look at the square at the bottom left hand side with a side length x, the area of that square is x by x, which is x squared. If we look at this square up at the top right hand side, it has a side length y, and so its area is y by y, y squared. So the sum of the shaded areas will be x squared and y squared. Now remember, this point A is movable up and down the line, and as we move it, the sizes of these two squares will change. But as A moves up and down, the value of x will move up and down with it, and so the formula for the area can remain the same. It'll always be x squared plus y squared. The important thing in this question is that x and y have a total value of 10, so they have to add to give 10. So what we're going to do is, we're going to do out a table of various values for x and y. So starting with the lowest natural number for x, 1, and moving up through 2, 3, 4, 5, and 6, we can see that the y values would have to be the number that would join with the x to sum to 10. So when x is 1, y would be 9. When x is 2, y would be 8. When x is 3, y would be 7, and so on. So if we then go and fill in areas for these values of x and y, so for the value of x equal to 1, we have a square that's 1 by 1, or 1 squared. And when x is 1, it would give a corresponding y value of y equals to 9. And so the area of this top right hand square would be 9 by 9, which is 81. So by putting them into the formula, we can see that the smaller squared would be 1 squared, and the larger square would be 9 squared, and 1 squared and 9 squared would be 1 plus 81, which is 82. Similarly, if we were to change the value of x to be 2, that means that this A point has moved up the diagonal, and it has changed the value of x to 2. And so now we have a square that is going to be 2 by 2, which is 4. So as the point A moved up and changed the value of x, it also changed the value of y. And so now we have a square that is 8 by 8. So if we put these numbers into the formula, if x is 2 and y is 8, well then the sum of the areas is 2 squared and 8 squared, which is 68. And so we can fill out this table for various values of x and y. We get 3 squared and 7 squared is 58, we get 4 squared and 6 squared is 52, and we get 5 squared and 5 squared is 50. So we can stop subbing in points at this stage, because any future values of x and corresponding values of y are just repeating sums that we've already found. 6 squared and 4 squared is the same as 4 squared and 6 squared. If we change x to 7 and y to 3, well 7 squared and 3 squared is the same as 3 squared and 7 squared. So anything after 5 and 5 is just repeating the values that we already have for the areas. So on inspection of the areas, we can see that they go from 82, 68, 58, 52, and 50, and then they would start repeating and go back up 52, 58, 68, and 82. And so the minimum value for the total area of the two shaded squares in this question is 50. One thing to say is that it's not a hugely definitive analysis of the problem, in terms of there are numbers we have missed from 1 to 2 and obviously from 2 to 3. We've only included natural numbers, but it is very clear to see the trend as we move down from smaller x values to the middle x value of 5, and then back up through the x values again where the areas start getting larger. For a really definitive approach to this, we could use a topic from Leaving Cert Maths called calculus, but for an exploration at Junior Cert, I think that the analysis that we've done here is absolutely fine. The B part gives us the same square, but they've also marked in the length of the diagonal of the rectangle, which they call D. They ask us to show that the value of the total area of the two shaded squares is equal to D squared. So we're going to go with the same notation as before, and we're going to mark in that the side length of the bottom left hand square is going to be X, and the side length of the top right hand square is going to be Y. So we can say that the sum of the areas of the shaded squares is once again x squared plus y squared. We can see that in the rectangle, the diagonal now forms a right angled triangle, and we know that the sides of this right angled triangle are x and y, as they're the sides of the two shaded squares. With a right angled triangle like this, when we have two sides and we're trying to find the length of the other side, we can use Pythagoras theorem. So x squared plus y squared would be equal to d squared. Now we've already established that the area of the two shaded squares is equal to x squared plus y squared, and now we're also saying that x squared plus y squared is equal to d squared, and hence the area of the shaded region is equal to d squared as required.